All right, going to be working here on the homework for 8.3, which is titled The Integral and Comparison Tests. So I am looking at page, well, this book is page 453, and I'm going to use the, I'm going to be starting with number 9. So let's see here. Get some good fresh markers here. Get these out of the way. Okay, so number 9. Number 9 says, use the comparison test. Use the comparison test to determine whether the series is convergent or divergent. So we have sum n equals 1 to infinity of n over 2n cubed plus 1. All right. Well, if I'm going to look at a different series to compare this to, what I first think about is how does this behave if n is very big? So if n is very big, the denominator really acts like, so this is what I'm thinking over here. This is something like this series. If n is really big, then this really just acts like n cubed. The plus 1 and the times 2 doesn't really make a difference. And then on the top, it just acts like n. So it looks like maybe it's behaving like 1 over n squared because n over n cubed is n squared. So perhaps this is what I should compare it to. And I know what this series does because if we look at our sheet, this is a p series where the p here is 2, which is greater than 1. And if the p is greater than 1, then it will converge. So this is convergent. This is a convergent series. This is what I want to compare that one to. And the comparison test says that if this series is always bigger than this series, or each one of these terms is always bigger than each one of these, then the sum of all of those pieces should be bigger than the sum of these pieces. So here's what I want to show. I want to show that, let me get my notation right here. They call this one the a sub n. I want to show that a sub n is less than or equal to b sub n eventually. All right. If I can show that, my conclusion will be, so I want to show that. If so, then the sum of the a sub n's will be less than or equal to the sum of the b sub n's. And we already know that this goes to some number. So that means that our series has to be less than or equal to some number, which means that our series converges also. So let me try and show this inequality is true. Now a sub n for me is this. Remember the one I'm comparing it to is this. So this is my b sub n. So I want to compare those two sequences and show that inequality is true. So let me go ahead and write that down. I want to show this. So I want to show that n over 2n cubed plus 1 is less than or equal to 1 over n squared. So what I'll do is what we did before when we were dealing with like monotonic sequences and things like that, and that's just use algebra to try and come up with some nice concrete conclusion that this is always true. So what I'll do is I'll multiply both sides by n squared. When I do that, it goes away over here, turns that into an n cubed. And I'll multiply both sides by 2n cubed plus 1 here, 2n cubed plus 1 here. And so that'll just give me 2n cubed plus 1. And so when I compare these, let's see, if I subtract, let me subtract n cubed, subtract n cubed. I get 0 over here is less than or equal to 2n cubed minus n cubed is n cubed, and then plus 1. And I believe this is always true because remember n is going to start at 1. So if n is 1, this is 2. If n is 2, this is 9. And obviously that's always bigger than 0. So my conclusion is that this is true, right? Therefore, since the sequence converges by comparison test, so does I'm getting kind of lazy with my n equal 1 to infinity here. So does this. Done. Okay? So notice I'm writing everything down. It's nice and logical. I had this. I thought about what I was going to compare it to. I identified what my a sub n and b sub n were, and went ahead and showed the inequality was true. Also, another thing I should point out is that in the comparison test, we have to have that a sub n is greater than 0, and we also have to have that b sub n was greater than 0. But that's true because this is always a positive number, because it's a positive number over a positive number. And then the other one I compared it to, this one, b sub n, that's always a positive number also. So that was true in my assumption. Probably should have stated that, but I'm stating it now. All right, let's do number 10. Same thing, sum, this time n equals 2 to infinity, of n cubed over n to the 4th minus 1 plus 1 plus 1 minus 1. Okay, so I think it says we want to use comparison test. So let me see, what would I compare this to? If n is really big, then that's acting like, the top is acting like n cubed. The bottom is really acting like n to the 4th. And so this is really looking like sum n equals 2 to infinity of 1 over n when I just reduce that out. So this is what I would want to compare it to. I do need to make sure that, well, I'll be a little more, be a little better with my notation here. I'm going to say a sub n is this one. And is that always greater than 0? Yes, because that's a positive number. And if n starts at 2, 2 to the 4th power minus 1, that number will always be positive. The ratio of two positive numbers is always positive. B sub n over here, 1 over n. And that's always positive. That's pretty obvious. So I'm going to be comparing those two sequences, but I need to know what this one does. Like if I'm going to compare it to something, I have to know what the thing I'm comparing it to does. So what does that do? Well, this is a harmonic series. We have 1 over a linear expression, or you could say this is a p series with p being 1, right? That's 1 right there. And so it's going to diverge. So this will diverges, all right? And if it diverges, then there's something a little different that I want to show. I want to show that a sub n is always bigger than or equal to b sub n. And my conclusion is that if so, then my series a sub n should be bigger than or equal to the series with b sub n. And if I know that that blows up and gets infinite, okay, or diverges, this one has to be bigger than that. That's also going to blow up. So I'm trying to force this one to blow up like this one does. Now let's see what happens. Remember, this is the inequality I need to show right here. If I can do that, then I know that since this diverges, that will. So let me go ahead and write down that inequality. I'll do it right here. I'm trying this. So I want to show a sub n is greater than or equal to b sub n. So I want to show that n cubed over n to the 4th minus 1 is greater than or equal to 1 over n. Do the same thing, multiplication, n to the 4th greater than or equal to n to the 4th minus 1. And if you subtract n to the fourth on both sides, you get 0 is greater than or equal to 1. Check, that's always true. Therefore, this inequality is true, and I can draw my conclusion. So here I come drawing my conclusion. Therefore, since the series n equals 2 to infinity diverges, sorry, equals to 1 over n diverges, so does, or I'll say, since that converges, the comparison test can't write, says this series also converges, diverges. So notice that what I'm going to be looking for in your work, especially on a test, is that you are stating out your conclusion. You're working through all the inequalities correctly, and you're drawing your conclusion and stating the test that you used here. And so it's very logical, easy for me to look at and grade. If you don't state what test you're using, and you just have a bunch of inequalities, you'll have points taken off. All right, let's do 11. Determine if it's convergent or divergent. So here we go. Sum, this is 11. N equals 1 to infinity. N to the 0.85, okay, 2 over n to the 0.85. Well, this is the same as 2 sum n equals 1 to infinity of 1 over n to the 0.85. And this right here is a p-series with p being equal to 0.85, which is less than 1. And because of that, if you look on your sheet for p-series, this would work with equal to, but if our p is less than or equal to 1, it diverges. So it diverges. And of course, 2 times the divergent series is still divergent, so this diverges by p-series. You could call it a test, I guess. That's pretty straightforward. Nothing to show there. You just have to identify what p is. Okay, 12. Sum n equals 1 to infinity of n to the negative 1.4 plus 3n to the negative 1.2 All right, well, I have the sum here of 2 terms, right? So I should be able to split this into 2 sums. But there's a little bit of an issue we run into here. Also, this is the same as 1 over n to the 1.4, then plus sum n equals 1 to infinity. And the 3, I'll put the 3 out here. And then 1 over n to the 1.2. So we are allowed to split this into 2 series as long as, and this is very important, as long as each one of these converges, then me splitting it up was okay. If it turns out that one of these diverges, then I couldn't split it up to start. So let's see what happens here. If I take this one, this is a p-series. P is 1.4, which is greater than 1, so it converges. Good. That's good to have because I know that I could split this one off. This one is also a p-series with p being equal to 1.2, which is greater than 1. Now, so that also converges. So if you add a convergence series to another convergent series, it's going to converge. So this one is a convergent, this one converges since it's the sum of two convergent p-series. There. So again, notice I'm stating my conclusion clearly. I'm stating why I'm drawing that conclusion. I have two convergent p-series, and the sum of two convergent series is convergent. So that's it. Let's look at 13. Notice I haven't used a comparison test yet. Let's see if 13 I need to. 13, all right, here we go. Now we're gonna have some fun. One plus 1/8 plus 1/27 plus 1/64 plus 1 over 125. Excuse me. I think I see this. Those are all perfect cubes. 2 cubed, 3 cubed, 4 cubed, 5 cubed, 1 over 1 cubed. Okay, so 1 over 1 cubed, 1 over 2 cubed, 1 over 3 cubed, 1 over 4 cubed, 1 over 5 cubed. So this is really just sum, n starts at 1 to infinity of 1 over n cubed. And I hope this is obvious. This is a p-series. P is 3, bigger than 1, converges. That wasn't too bad. It's just really on that one, it's just finding the formula correctly. 14. 1 plus 1 over 2 root 2 plus 1 over, I'm going to guess 3 root 3 plus, I'm going to guess 4 root 4, yeah, 5 root 5. Did I do plus dot 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 on the last one? I don't know if I did. If I didn't, sorry. All right, well, that first one here looks to me like 1 over 1 root 1, 1 over 2 root 2, 1 over 3 root 3. So it looks like I just keep on going up, 1, 2, 3, 4, 5, and it's just the number and then times the root. So sum n equals 1 to infinity, 1 over n root n. Yeah. So now let's just do some algebra. This is just sum n equals 1 to infinity of 1 over n times n to the 1/2. That's what the square root means. And that's just sum n equals 1 to infinity of 1 over n to the 3/2 when you add the exponents, right? 1 plus a half is 3/2. And again now, this is a p-series. This is p being 3/2, which is greater than 1. Therefore, it converges. All right. So far, there's not really been much trouble here. Only really done the comparison test twice. See, 1/5 plus 1/8 plus 1/11, 1/14. Notice the denominator keeps going up by 3 each time, but it starts at 5. So how can I create that How can I create the sequence 5, 8, 11, 14, 17? How can I create that? Well, I know that I'm going to have a 3n there because each time I go up by 3, but I want my first one to be a 5. So if I plug 1 in here, I need 5, I need to do 2. So let's see, if I plug in 1, I get 5. If I plug in 2, 6 plus 2 is 8. If I plug in 3, that's 9, plus 2 is 11. So really what I did is I took 1, 3, 5. No, you know what? I won't do it that way. I think I made enough sense. I don't want to confuse you. All right, so that should be it. I should have this equals sum, n equals 1 to infinity, and then 1 over 3m plus 2. Now, on a test, I would just say, hey, look, at this point you could say it diverges because it's a harmonic series, because this is linear and this is a constant. But because this is the section on comparison test, I'm going to do a comparison. So let me try and compare that. I'm going to compare, I'll do the comparison one in red. I'm going to compare that to what? Well, the top, as n gets big, top just stays at 1. The bottom really just acts like n. And I know that this is harmonic. Or you could say p series with p being 1, which of course diverges. They're the same thing. All right, so I know this is a divergent series. So the comparison I need to do with this and this is I need to show that these guys are always bigger than these guys. So I need to show that 1 over n, 3n plus 2 is bigger than or equal to 1 over n. Also, I need to write down here, I'm looking at a sub n being 1 over 3n plus 2. I'm looking at b sub n being 1 over n. Both of these are greater than 0. Obviously, if n is positive, these are both going to be positive numbers. So I've checked that. I can use the comparison test. Let's go ahead and do our work here. When I do my cross multiplication thing, I get this, and then something bad happens. Watch. If I subtract n, I get 0 greater than or equal to 2n plus 2, and that is not true. If n is 1, this isn't true. If n is 2, it's not true. These are never going to be below 0 or equal to 0. So I've hit a catastrophe here. This is not working. I mean, we know this diverges. We know it does. But this comparison that I used, for some reason, did not seem to work out here. So let's think about how we might be able to tweak this so that it would work. What was the problem that I had when I did this? When I subtracted n on both sides, I got what do you get? 0 over here, and I still had n's over here, and that's going to get bigger. So wouldn't it have been better if I had n's on this side, and that way these n's got bigger and this side didn't get bigger? So how could I make more n's be over here? Instead of just n, I need maybe like 4n. And that way if I had 4n here, I subtract 3n, this n would get bigger than that side. So to get 4n here, I would have needed that down there to be a 4n. So let's go back here and tweak the problem. Hopefully you see that. If this is 4n, then when I cross multiply, that's 4n. We do our subtraction, it would go the other way. 3n out here, 3n out here, we get an n here, and then bigger than on this side, the only thing that would be there would be 2. And n is bigger than 2 eventually. Okay, so I'm tweaking things here to make things work for me. I'm going to come back to this. I'm going to change this. We said a 4n would work here. 4n. Now, is this still a harmonic series? Well, yeah, because that 4 you could really pull out as a 1/4, like that. And then you could say, well, that's harmonic, that diverges. 1/4 times that doesn't matter. It's still the same, diverges. So I'm going to compare it to that. I'm still going to say it's a p series with p being 1, it diverges. But now, over here, I change this to b sub n is 1 over 4n. And then my inequality is going to change. I still want to show this is true. So this is now 4n here. So now I multiply, I get 4n bigger than or equal to 3n plus 2. And then when I subtract 3n on both sides, I get n is greater than or equal to 2. Now, we all agree that this is not true right away. When n is 1, this isn't true. But what the important thing about the comparison test is that we need this inequality to be true eventually, like at some point, and then after that point, it's always true. So this would only work, right? This inequality would only work when n was bigger than 2, right? If n is 2, it's true. If n is 3, it's true. If n is 4, it's true. So eventually, this is true, which means that our series is always bigger than or equal to this series, and if this series goes to infinity, so does that one. So I'm going to draw my conclusion. Therefore, since sum n equals 1 to infinity of 1 over 4n, which is equal to 1/4 sum n equals 1 to infinity 1 over n, since this thing diverges, so does our series. By comparison test. I'm using kind of different language in each problem the way I'm writing my answer, just so you can see there's some flexibility here as long as you get your point across. Since the original, since the series I was comparing it to was divergent, and this inequality held, my series is divergent also. Remember though, I said on a test, all you have to do is show that first part. Well, is show the, if this problem were on the test, you would just say, hey, that's harmonic, we're done. But I'm showing you how the comparison test would work for that. All right, next one. Number, where are we? That was 16? No, what was that? Did I miss 15? Uh-oh. I forgot to do 15. Darn it. Well, that's okay. I think I might not do 15 because I think 15 is almost exactly the same as the other one, 16. Hey, those are all odd numbers on the bottom, starting with 1 down here. So this is sum, and whoa. Sum n equals 1 to infinity of 1 over, how do we create the odds? Starting at 1, 2n minus 1. And, okay, I guess I'll work it through. Shoot, I'm here, right, as well? All right, so if I looked at this, check it, it does work. This looks harmonic, okay, so it's going to diverge, and that's what you would say on a test. But if you're going to compare it, what we're going to compare it to is what we get when n gets real big. When n gets real big, this really looks like 1 over n. And that's harmonic. So I'm just going to run through this one real quick. This is harmonic. It's p series with p being 1. We know it diverges. We want to show that this, which is my a sub n, is always bigger than this, which is my b sub n. So I want to show that 1 over 2n minus 1 is bigger than or equal to 1 over n. And if we do this thing again, you're going to see it's not going to work. N greater than or equal to 2n minus 1. And when we subtract n on both sides, we get 0 bigger than or equal to n minus 1, and that's not true. So we run into the exact same problem we ran into on 16, and that's we need to tweak this. So hold on just a second. Okay, so now, if I want to tweak this, remember, I want to make this end bigger than this one so that this side's bigger than this. So I think the safest bet would try and make that a 3. which means make this a 3, which means make this a 3. But then that's still the same as this, which is still divergent. So look at my solution for number 16 I did before this. It's pretty much the same thing. We tweak it, and so you'll get the same conclusion, that this diverges. Okay. I also could have used like 5n here, 10n, it wouldn't matter. As long as I make that left side bigger than the right side, I would have been in business. All right, next one, number 17. I really do hope that you're trying these on your own before you're going to these videos. Watching me do it's a lot easier than you doing it. Okay, n times e to the negative n. Let me first write this as a fraction. So when I look at this, if n gets really big, you know, the top looks like n and the bottom looks like e to the n. There's not a whole lot more I can say about that. You might think, okay, well, n is linear and this is just huge exponential functions. So maybe I could compare this to something like sum n equals 1 to infinity of 1 over e to the n. You could maybe compare it to that. But then you'd have to figure out what type, you know, what does this one do? And if you look at this, this is actually 1 over e to the n, like that. And this is a geometric series with the base 1 over e, with r being 1 over e, which is less than 1. And so I know that this converges. I don't need to go figure out what it converges to, but I know that this converges. So let's try this. Let's try comparing this to this. And I don't know if this is going to work. So what do we need to show? What do I want to show if I want to show that my series also converges? I have to show that my series is smaller than that one, right? If this is bigger than that, then it could be infinity. So I have to make sure that this one right here is bounded by that series. So that means I need to make sure that this right here, a sub n, is always less than or equal to b sub n this time. So I want all of these to be less than all of these, or that's the same as this. This is my b sub n. Also, these are both greater than 0. Just look at them, let n be 1, 2, 3, 4. That's going to always be positive. So let's show this. And like I said before, I don't know if I'm going to be able to do this. So this less than or equal to 1 over e sub n. And when we do that, what happens? You get multiply across this side, you get n, e to the n, less than or equal to e to the n. Sorry, I don't know why I did that. I multiply both sides by e to the n, so this is 1 on this side. And that is not happening. So look, I don't know where my brain just went. Sorry about that, it's back. I multiply both sides by e to the n. I get n is less than or equal to 1. That is not true. And only, I mean, when n is 1, yeah, it's true, but when n is 2, 3, 4, it doesn't work. So this comparison doesn't appear to be working for me. What else could I do? Really, I don't see a way of making this side smaller than this side, like we did in the previous problems, like where we just came in with that 3 to make the ends work better. I can't seem to do that on this side, because if I make this like 4n, it's still not going to be true. What does that mean? It means that my comparison series didn't work. I need something else. I cannot say Just because this one converged and this inequality I couldn't get to work the way I want, I can't say, oh, okay, then it diverges. Can't say that. It's just that my comparison series sucked. Okay, it wasn't good enough. It didn't let me draw any conclusion. So the test failed, and I need to try something else to compare this to. So I have to start over, basically, is what I'm saying. Okay, so since that didn't work, I don't really see another series that I want to compare it to. So let me kind of go back to the beginning and think about what else is this section about. This section is also about the integral test. The integral test says that if we look at this series, right, and if we convert this sequence into a function of x, then if f is continuous on where is n starting? 1 to infinity. And f is positive on 1 infinity. And f is decreasing eventually so if we've got a function, if we turn this sequence into a function of x, so on the real numbers instead of just the 1, 2, 3, 4, 5, the integers, then as long as that's a continuous function, and as long as it's positive, so every time we plug in an x we get a positive number, and as long as it's decreasing, it's going down, then if the integral from 1 to infinity of f of x dx converges, so does that. If this integral diverges, so does that. So we have a lot to look at here. Can we even integrate this? Because we'll need to. Can we integrate this? So you look at that and you go, oh, well, wait, hold on. We did this like integration by parts. I think we can integrate that because we can use our ultraviolet minus voodoo to kill off the x, and then we'll have something nice in the other integral. So we should be able to integrate that. Is it a continuous function? Well, let me rewrite this. X over e to the x. X is a continuous function. E to the x is a continuous function. The quotient of two continuous functions is continuous as long as we never have division by 0. This is never going to be 0. E to the x is never 0. So you're never going to get division by 0. So it is continuous. Is it positive? I need to check. Is it decreasing? I need to check. So there's a lot of work to do in this. So here we go. I'm going to do it formally now. This was just me thinking. Okay. Let f of x be equal to x e to the negative x. Is f continuous on 1 infinity? Yes. It's the quotient of two continuous functions. Okay, first part's done. Is f positive on the interval 1 to infinity? Well, let me check. What does that mean? Is x e to the negative x greater than 0? Is it greater than 0? Well, again, we can look at it this way. Is that true? Well, as long as my x's come from 1 to infinity, as long as these are positive numbers, that numerator will be positive over that e to the any number is positive, and that is greater than 0, so that checks. So I've got the second thing. These are conditions I need to verify before I can use the integral test. Now, is it decreasing? is it decreasing? Is f decreasing on 1 infinity? I forgot my question mark here. Well, to show it's decreasing, I'm going to want to show that the derivative of f is less than 0. Actually, this decreasing, it doesn't necessarily have to be decreasing the whole time. It's just eventually has to. Let's see. Okay, eventually. So it's like if I draw a function, it may go up. Eventually, it needs to come down and keep going down forever. So maybe over here it's increasing, but eventually after some point right there, it's decreasing from there on out. That's what we need. And this doesn't have to be 1. 1 can be back here. This could be 5, and eventually it goes down. So let's see. Well, I need my derivative. So what's the derivative of x e to the negative x? Well, I can use the product rule. Derivative of x is 1 times e to the negative x, plus derivative of e to the negative x, which is e to the negative x, times negative 1, because that's derivative of what's up here, times the x from the front. So we're getting, let's see, I can factor in e to the negative x out of both. 1 minus x. So my question is this less than 0? So let's check it out. I'm at a room here. So is that less than 0? Well, this right here, I'm going to rewrite as 1 minus x over e to the x, dropping this down. Is that less than 0? Question. Well, what do we know about the numerator? If x is 1, this is 0. If x is bigger than 1, then this is going to be bigger than 1. So 1 minus this number should be a negative number. So I should get a negative number on top. E to any number is positive. Negative divided by positive is always less than 0. This is true if x is greater than 1. But that's good because that's what we wanted. See, at 1, I don't care that it is 0. I don't care that it's 0 at 1. Bigger than 1, so eventually this inequality does true and it holds the rest of the way. So yes, the answer is yes, we have a decreasing function. So we've got everything we need in order to use the integral test. Now we get to use it. So let's figure out what the integral of this thing does. What is the integral from 1 to infinity of x e to the negative x dx? So I'm going to use integration by parts. I'm going to first just look at the indefinite integral over here. U dv, let u be x, dv be e to the negative x dx. Differentiate down, integrate up. Careful with that negative, you have to account for it out there. So this is going to be ultraviolet minus integral of voodoo, which is this times this. And notice that negative there, times this. I'm going to bring that negative and make it a positive, e negative x dx. And then this turns into negative x e to the negative x. Antiderivative of that is negative e to the negative x. So that's my antiderivative. So over here, I get, now notice we have an infinite limit. So I've got limit as t goes to infinity of integral 1 to t of x e to the negative x dx, which equals now the antiderivative. So limit t goes to infinity of negative x e to the negative x minus e to the negative x evaluated from 1 to t. And I don't really care for this version of it. I'm going to do something a little different. I'm going to do limit t, well, you know what? T goes to infinity. I'll go ahead and do it right now. All right. So if we plug in t, we get negative t, e to the negative t minus e to the negative t. Okay, if we plug in 1, we get, so minus, if we plug in 1, we get negative 1, so negative e. Negative negative 1 is 1, so 1. And then minus, again, 1 in here. Wait, did I say negative negative 1? Oops. I'm plugging in 1. 1 goes in there. 1 goes in there, okay. Minus e to the 1 again. Close that off, and then the limit. All right. Gosh, man, I'm making all sorts of mistakes on that. You know what? I said I was going to switch it. This is right, but let me switch it because I really don't like the way that looks. I just don't like it. So I'm not going to actually do the t and the 1. What I'm going to do is rewrite this first. And watch how I'm going to rewrite it. I'm going to pull out an e to the negative x. Let's make it a negative e to the negative x. I'm left with x plus 1 if I do that. And then I'm going to take this and drop it below as a positive x. And then, you know what, I had that negative. Maybe I'll just leave it out there, negative like that. So this is going to be a limit, t goes to infinity, negative x plus 1 over e to the x evaluated 1 to t. I like that a little better. So now, limit t goes to infinity of, let's see, t goes in first. I get t plus 1, so negative t plus 1 over e to the t minus, now I plug in 1. I get 1 plus 1 is 2, so negative 2 over e to the first power, so that's that. Now let's let t go to infinity. If I let t go to infinity, this becomes infinite. E to the infinity also goes to infinity. I get infinity over infinity. So I can actually use L'Hopital's rule here. L'Hopital's rule says that I just need to take derivative of the top and bottom separately. The derivative of the top here, right here, is just 1, and then there's a negative. And derivative e to the t is itself. Minus, now I'm not touching this one. So I really just did L'Hopital on this. And now as t goes to infinity, this goes to fixed number over infinity, that goes to 0. And so my answer is going to be this together, it's plus 2 over e. So this integral goes to 2 over e, which is a number. It converges. And since this converges, my series converges. Now, I'm not saying that my series goes to this. I'm just saying that my series converges. So, therefore, since the integral 1 to infinity of x e to the negative x dx converges, so does the sum n equals 1 to infinity of n e to the negative n by the integral test. Done. It's a lot of work. It's a lot of work for that problem. All right, how's my time here? 48 minutes. Let me see if I have time for another one. Yeah, let's do 18. Okay. Sum n equals 1 to infinity n squared over n cubed plus 1. All right, so if I were doing this problem, initially, I would look at it, I'd say, okay, I want to compare that to something. I would like to compare that to this. N squared over n cubed, because that's what it's really behaving like, which is 1 over n. This is a divergent harmonic series, so I would do my comparison. I would need to show that that is bigger than this. The n squared over n cubed plus 1 is bigger than this. So real roughly, let me just lay out how this would be working, although I'm going to do it a different way. I would need to show this. And if you did it, n cubed greater than or equal to n cubed plus 1. And then this, when you canceled, you would get 0 is greater than or equal to 1, and that's never true. And so you could tweak it. You could try and make this side bigger than 1, and you could do it. You'd probably have to come in here, maybe like with a 5. That would make this a 5. And then when you do your subtraction, it would work. And so it could be done that way, and I'm not saying not to do it that way. But I wanted to show you that you could also do this using the integral test. So let's see. Integral test, the reason why I'm thinking integral test is because I know that if I convert this over to a function, if I let f of x be equal to x squared over x cubed plus 1, I can integrate this pretty easily because I can let u be the bottom, the derivative of that is up there almost. So I have basically a basic substitution on this, which is nice. The problem is that I have to show f is continuous. Is that true? Well, continuous function over continuous function. Yes, the only time the bottom can be 0 is if x is negative 1, but that's not where we're looking. So this is a continuous function on the interval 1 to infinity, that's fine. Is f positive? Well, that's a positive number over a positive number as long as x is bigger than or equal to 1. So yes, on 1 infinity it is. And then the next thing is f decreasing? So in order to show that, eventually, right, I need to look at the derivative of this. And I just use a quick quotient rule on that. 2x, x cubed plus 1 minus 3x squared times x squared. There's my quotient rule all over the bottom squared. So this is 2x to the 4th plus 2x minus 3x to the 4th over x cubed plus 1 squared. And when I put those together, let's see what I get here. 2x minus x to the 4th over x cubed plus 1 squared. I can factor an x out of the top, x, 2 minus x cubed over x cubed plus 1 squared. So there's my derivative. The question is whether or not that's negative. So is f prime less than 0 eventually? So is that less than 0? Let's see. X times 2 minus x cubed over x cubed plus 1 squared. Is that less than 0? Well, I know the bottom is always positive, right? Because I'm squaring it right there. So I know the bottom is positive. It really doesn't play much of a factor here. I know that if I'm plugging in things like from 1 to infinity, I know that this right here is positive. The only question then is this piece right here, 2 minus x cubed. I need this to be negative, because then I'll have a negative times a positive. That'll be negative over a positive, that's negative. So the question is this negative? Well, if x is 1, no, right? That's going to be just 1. If x is 2, though, I get 2 cubed, that's 8. 2 minus 8, that's negative. So from 2 on, it's going to work. So is f decreasing? Yes, eventually it is. It's eventually decreasing. I won't say where, but it just eventually is. It's after 1 somewhere. So I have everything I need to use the integral test. So I need to find the integral. So I look at the integral from 1 to infinity of x squared over x cubed plus 1 dx. Convert this over just to an indefinite integral real quick so I can find the antiderivative. Make a basic substitution of the bottom. There's du. 1/3 du equals x squared dx. So I'm going to replace x squared dx by 1/3 du. I'm going to replace x cubed plus 1 with u. So this integral becomes 1/3 1 over u du. And then that becomes 1/3 natural log absolute value u. Plus c, but we're going to come back up here now. So this becomes I better do it over here. That becomes limit t goes to infinity, because I have that thing up here. The antiderivative of this is this, 1/3 natural log, but what was u? U was x cubed plus 1. Evaluated from 1 to t. And now, when we plug in, limit t goes to infinity. Let's plug in t first. 1/3 natural log absolute value of t cubed plus 1. And then minus 1/3 natural log. When we plug in 1 here, we get 1 cubed plus 1, that's 2. So natural log of 2. And now let's let t go to infinity. If t goes to infinity, this is infinite. Natural log of infinity goes to infinity times 1/3. So this whole thing goes to infinity minus whatever this number is. And that's going to go to infinity. And that means it diverges. That's a g. So therefore, since the integral from 1 to infinity of x squared over x cubed plus 1 dx diverges, so does the integral from, not the integral, the sum that we're looking at, this sum, the series, sum n equals 1 to infinity of n squared over n cubed plus 1. Why? By the integral test. So I think you can say pretty easily on this example that it would be preferable to do this problem the first way I showed you, by using the comparison test. But I'm just showing you that for this particular problem, and a few of the ones we did before, we could have used the integral test to do it. Where am I at? 10, 15, 7. I think that's good. I'm going to put a little mark on my page here. I finished up on 18, so I'm going to start. Okay, ended on 18. I will start with 19 on the next video when I have some time for that. Okay, I'll be picking up here 8.3, starting on number 19. All right. So let's see what we've got here. Sum n equals 2 to infinity of 1 over n natural log n. All right, well, I see something right away. I see that if this were an integral, the derivative of natural log of n is 1 over n, which I have right here. So I'm already starting to think integral test. I could do comparison test. The question would be, what do I want to compare that to? Let me go with the integral test. I think that's where we'll have the most success here. Not to say that a comparison test won't work. So what do I need? First of all, I need to convert the series, right, and the sequence in here to a function of x. And then I need to check some conditions first before I can apply the test. So is f continuous on the interval 1 and infinity? Well, actually, I only need to look at 2. And let's see, I just got to make sure there's nothing. Oh, I forgot to put that as an x. Got to make sure that I plug in 2. I don't get division by 0 here. So 0 would give me division by 0. It's not in here. And then natural log of 1 is 0. So, well, 1's not in here, so I should be okay. The next thing I need is to make sure that n is positive. That f is positive. So is f positive on to infinity? Well, if I'm plugging in positive numbers, that's going to be positive. Natural log, well, we do get negatives with natural log. Remember, the natural log function looks like this, but this is at 1, and so after I get past 1, the natural log function is positive. So I know that this is also positive. And then now I need to show that it's decreasing. So f decreasing. It's positive, it's continuous, eventually, right? So let me take the derivative there. F prime of x equals, now there's several ways you could do this. I guess I'll just use quotient rule. The derivative of the top is 0 times the bottom minus the derivative of the bottom, that's a product rule. Derivative of x is 1 times natural log x plus derivative of natural log of x is 1 over x times x. So that's my product rule. And then times the top all over the bottom squared. And let me figure out what that is. So f prime of x is equal to, let's see, this goes away. I get negative to distribute through, negative natural log x. 1 over x times x is going to give me 1, but I distribute a negative through, so negative 1. Over x natural log x squared. Now, the bottom is always positive. In the numerator, well, natural log of x, I know that this piece right here is always positive as long as I'm past 2, or past 1 in fact, but I'm starting at 2. So that's always positive, and then make it negative. So negative number minus 1 is still negative. So I have a negative over a positive. That checks out. That's negative. So my function is decreasing. Now, once I've satisfied all the conditions for the integral test, I need to make sure I can integrate this. So let's try this integral. I'm going to do the integral from 2 to infinity of 1 over x natural log x dx, which is the same as the integral from 2 to infinity. Let me write it this way. 1 over natural log x times 1 over x dx. I'll make a u substitution here. U is natural log x. du is 1 over x dx. So I have du right here. This is 1 over u. So this integral becomes, actually, you know what? Let me do the indefinite integral first, because I'm going to switch it to u. So this integral becomes integral 1 over u. This is du. And the antiderivative of 1 over u du is natural log of the absolute value of u, plus a constant. But what was u? U was natural log of x. Huh, interesting. So here's what we've got. We've got integral 2 to infinity of 1 over x natural log x dx equals the natural log of x evaluated from 2 to infinity. Now I should be using a limit here. So let me go ahead and do that limit now. So I have that this equals limit t goes to infinity of natural log of x evaluated 2 to t, and then limit t goes to infinity, and then when I plug in t, I get natural log of t minus when I plug in 2, I get natural log of 2. All right, and now let t go to infinity. As t goes to infinity, we get natural log of infinity, which is infinity, natural log of infinity again, which is infinity. So this is becoming infinite minus, this is a number, it doesn't matter. So this thing is diverging. So therefore, by integral test, our series does whatever the integral did. So it diverges. And that's it. All right, let's take a look at number 20. Okay, for 20, sum n equals 1 to infinity of n squared minus 1 over 3n to the fourth plus 1. Let's see if I can get a better marker. That's a good one right here. All right, so let me see here. If n gets really big, this looks like I can compare it to sum n equals 1 to infinity. The top's acting like n squared. The bottom's acting like, I'll put 3n to the fourth. I could just put n to the fourth, but I'm going to put 3n to the fourth, which is really just sum n equals 1 to infinity of 1 over 3n squared. This is a p series, with p being 2, which is greater than 1, which means it converges. Remember, the 3 here could come out as a 1/3, and it would still converge. So I've got a convergent series that I think this one compares to. So what is it that I want to show if I'm comparing my series to a convergent series? Well, I want to show that my sequence, a sub n, always stays smaller than or equal to b sub n, where b sub n is this one. I'll also check real quick. If n is 1, this is 0. If n is 2, that's a positive over a positive. So this is greater than or equal to 0. It's, definitely at 1, it's 0, but past that, it's going to be positive. And then over here, this is always greater than 0. So we're going to be able to use the test. So let me see if I can show that this is true. Remember, if all of these are adding up and they're converging to a number, then if my numbers here are smaller than these or equal, then mine should add up to be a number also. So I want to show that n squared minus 1 over 3n to the fourth plus 1 is less than or equal to 1 over 3n squared. And then I do some, algebra here. Let me see, if I multiply both sides by 3n squared, it goes away over here. It becomes 3n to the fourth minus 3n squared, less than or equal to, this times 1, 3n to the fourth plus 1. So let's see, if I subtract 3n squared, or 3n to the fourth on both sides, it goes away. And what I'm left with is negative 3n squared is less than or equal to 1. And this should always be true. You could just switch them. You can move, add this to this side. You could get, or not even switch them, just move this to the other side. You get 0 on the left side. On the right side, you get 3n squared plus 1. And this is always true. As long as n is a positive integer, we're good to go. So we've shown that it compares, so we're ready to draw our conclusion. Therefore, our sum, n squared minus 1 over 3n to the fourth plus 1, converges by comparison test. So I wasn't thinking integral test here, because if I were to imagine this being an integral, that's not something that I'd really want to go after. It's, I'm sure we could integrate it, but it would just be a lot uglier than this was. All right, let's look at 21. Sum n equals 1 to infinity. Cosine squared n over n squared plus 1. All right, so that cosine squared n on top starts to make me think of something like a squeeze theorem. Oh shoot, am I not recording? Where's my audio? I hope I've got audio. Yes, I do, okay. That was a little bit scary. I noticed that my cosine squared n, I know that that has always got to be between 1 and 0, right? Cosine is always between -1 and 1, but if you square it, it's got to be positive or it could be 0. So I know that. So the top is really like, I mean, you could look at it when you're trying to compare it to something. Maybe this is something like a 1 over n squared plus 1. Yeah, it's worth a shot, right? I mean, try and compare it to that. I don't want to integrate that. I really don't want to integrate that because I've got cosines mixed with a polynomial. That would probably be pretty ugly. So let me try and compare it. So let's see what my comparison series would be. Maybe sum n equals 1 to infinity. Maybe 1 over n squared plus 1. So what is this? You'd have to know what this is. Well, if that wasn't there, that's a p series. And that would be p being 2, and that would converge. Adding 1 to the bottom is not going to change the convergence. You could check this for yourself. That we could go and do a comparison of this to this and figure out from a comparison test that this converged and that converged. You could also do an integral test on that to show that that converged. But because we're adding just a constant onto this down here, it doesn't have an n here, we'll be happy to just say, hey, look, that's basically a p series. It's a p series with p being 2. So p series, p is 2, greater than 1, converges. So I'm going to be comparing the sequences to each other now and hoping to get an inequality to work out here. This is going to be my b sub n. It's greater than 0. This is my a sub n, and that's also greater than 0. Could also be equal to 0, depending on whether or not that cosine turns out to be 0 on top. But they're both positive, or they're both non-negative, so we should be okay here. I want to show, since that one converges, that my a sub n's stay less than or equal to my b sub n's. So I want to show that cosine squared n over n squared plus 1 is less than or equal to this one, which is 1 over n squared plus 1. And if I multiply both sides by n squared plus 1, I get cosine squared n is less than or equal to 1. We already knew that that was true, right? We talked about that earlier. This is always greater than or equal to 0. So this should always be true. So I'm good. So that's going to converge. Therefore, series n equals 1 to infinity, cosine squared n over n squared plus 1 converges by comparison test. Now, I do want to show this. I mean, I'm done here, but I do want to take a moment to take a look at this. Let's show that this one converges. I really want to kind of convince you that this one converges. Even though we say it's a p-series, that plus one does have an effect on things, but I want to convince you that's not going to matter. Maybe I can do it in a general way. No, that might be a little bit more than I want to do here. Let's try and take that as its own problem. Okay, and what I'm going to do is I'm going to set up a function. I'm going to do integral test. I'm going to do this. This is obviously continuous. It's positive. And is it decreasing? Well, if I take the derivative of this, let's see what we get. I would actually do quotient rule, so derivative of the top, which is 0, times the bottom won't matter, minus derivative of the bottom times the top over the bottom squared. This is definitely a negative number on top. As long as x is positive, this is a negative number. The bottom is always positive. So yeah, that checks out. This means f will be decreasing. And now I just need to be able to integrate it. So I've got everything I need. So I need to do the integral from 1 to infinity of 1 over x squared plus 1 dx, which is going to be arctangent of x. That look familiar? 1 to infinity. Now I need to set up a limit, but because I'm just real quick sketching this out for you, let's just think about this. If I'm going to plug in infinity for this, the arctangent of infinity, remember we've done this a lot, is pi over 2. And then minus what we get when we plug in 1, so tangent inverse of 1 is pi over 4. But the most important thing is that this is a number, and that converges. So this integral converges means that converges. So it worked. Okay? So I guess the moral of the story is this, and maybe I'll mention this in lecture, I don't know if I will for sure, but if you have something like this, sum n equals 1 to infinity of 1 over n to the p plus some constant, that this, if p is less than or equal to 1, it will diverge. If p is greater than 1, it will converge. So having a constant out here, like that's a p-series, having a constant out there has no effect on anything. It's still going to hold true. Hey, you're welcome to come in, but you got to give me half an hour.
No,
Is
I
that
just want to ask.
Oh, sure.
Am I able to, you think I'll be able to take the test right now? Or is there going to be telescopic questions on the exam? Because on the homework there's only one.
It covers all through series. I'm pretty sure there's telescopic on there.
Yeah, because on the homework there's only one, and I was able to get that.
If you could do the one on the homework, you should be okay.
Okay.
Yeah.
Yeah, because I want to knock it out.
Yeah.
Pretty complicated.
Yeah, if you feel good about it. As long as, I'm trying to think, I pulled all the exam problems from the homeworks.
Oh, okay.
So if you were okay on the homework, you should be okay on the test.
Okay.
Yeah, it's not due till what, Saturday?
Yeah.
Yeah, so okay, yeah. I decided I'm not going to try and push anything past 8.2 on that test. So you should.
Well, Saturday I was able to do all of 8 too, so
Okay, good.
the homework, so.
Okay,
So,
yeah.
I actually like it.
That's cool. Good, good, good.
See you later.
Okay, I'll be here. I'll be around if you need me. Okay. All right, let's move on. 22. 22. Sum n equals 1 to infinity of 4 plus 3 to the n over 2 to the n. Well, my instinct here is to try and split this up into 2 and make it like 4 over 2 to the n plus sum n equals 1 to infinity of 3 over 2 to the n. So these were both to the n, so I put them together. And then over here, I could take this 4 out, make that a 1. Here's the problem I'm going to run into, though, is that this right here, okay, if I look at this right here, well, let me rewrite it. 1/2 to the n. That's a geometric series. I need to tweak it a little bit to get an n minus 1 here, but that's a geometric series. The r here is 1/2. That should converge, so that's okay. This one, though, is geometric, and the r here would be 3 over 2, which is bigger than 1. That would diverge. So I'm not really allowed to split it up unless they both converge. So I need to really come back here and just make sure that this over here doesn't, that I can't tell it diverges from just this. So let's see here. Let's do a comparison. Let's compare it to this. Let's compare it to, I hope you understand, if I can only split up a series into 2 separate series if they both converge. If one of them diverges, you're not allowed to split them up, all right? So I'm going to compare it to this, because I think this thing diverges. I'm going to compare it to this, because that's really, this is this with the 4 taken away. And we know that with this 4 here, it makes my numerator a little bit bigger than the numerators over there. And so all of these should be bigger than those, and I already know that diverges. So perhaps that's enough. So I'm comparing to this. This is a geometric series. I do not need to find out what its sum is, okay? I don't need to go through and tweak it. I just need to look and notice that this is my r. And if it's a geometric series, the absolute value of r here is equal to 3/2. That's bigger than 1. This is going to diverge. So now what I'm going to do is I'm going to be comparing this thing, which is my b sub n, to this thing, which is my a sub n. And remember, what I'm trying to show now with the comparison test, since this one diverges, I need all of these to be a little bit bigger than those. So I need my a sub n's to be bigger than or equal to my b sub n's. So let's check it. Is 4 plus 3 to the n over 2 to the n greater than or equal to this, which I'll write as 3 to the n over 2 to the n. So I multiply both sides by 2 to the n, and they go away. And I'm left with 4 plus 3 to the n greater than or equal to 3 to the n. Subtract 3 to the n on both sides, I get 4 is greater than or equal to 0. That checks, so this holds. Therefore, the series n equals 1 to infinity of 4 plus 3 to the n over 2 to the n diverges by comparison test. Sum n equals 1 to infinity. Oh, okay. N minus 1 over n 4 to the n. There we go. Interesting. I'm not thinking integral test here, because if I do integral test, I don't want to integrate that inside. That looks too ugly. Well, comparison, what do we want to compare it to? If n gets really big, the top acts like n, the bottom acts like n. So let's just think about that. If we look at n getting really big, the top really behaves like n. This bottom here behaves like n 4 to the n, and these n's would cancel, which means this really looks like it might be behaving like 1 over 4 to the n, which is really just 1/4 to the n, which is geometric. It's a geometric series with r being 1/4, which is less than 1, which means this converges. So I'm thinking that this converges, and I'm going to compare it to this convergent series. And this is the one I'm going to be looking at right here. This is my b sub n. This is my a sub n. This is greater than or equal to 0. This one is actually always greater than 0. So what I want to show, think through this again, if this one converges, then I want all of these to be smaller than these. That way they add up to be something less than whatever that is. So I'm going to try my inequality a sub n less than or equal to b sub n. So I want n minus 1 to be over n 4 to the n to be less than or equal to 1 over 4 to the n. Let's multiply both sides by 4 to the n. Like that. Let's multiply both sides by n. And we get n minus 1 less than or equal to n. Subtract n on both sides, we get negative 1 is less than or equal to 0. That's true. So this holds. Therefore, my conclusion is that my original series converges by comparison test. So therefore, converges by comparison test. You may get tired of writing this over and over, but that's what I'm looking for. You need to draw it all, write it all out, explain every step, and then draw your conclusion at the end. Okay. Sum n equals 1 to infinity. One over cube root of n cubed plus 1. Is that right? Oh, square root. Square root. All right. This one looks a little troublesome. So I'm not thinking integral test again because I don't really want to integrate that. Maybe if that were n squared I would, but it's not, it's n cubed. So if n gets really big, what does this behave like? The 1 really won't matter anymore, will it? So this really looks like it's going to behave like 1 over 1 over the square root of n cubed, which is really just 1 over n to the 3 halves. And that's a p series. P is 3 halves, which is greater than 1, which means this converges. And so I'm going to be wanting to compare, well, either one of these. B sub n, it's greater than 0, obviously. I want to compare it to this, which is my a sub n, which is again greater than 0. And what I want, since that one converges, for this one to be smaller than that one. So I want to show A sub n is less than or equal to b sub n. So I want to show that 1 over the square root of n cubed plus 1 is less than or equal to, I'm going to use the top one up here, 1 over the square root of n cubed. Huh. All right. Let me just cross multiply and get this. I don't like using the term cross multiply. What I'm really doing is clearing fractions on both sides, but students seem to like that when I say that, so I'll stick with that. All right, so this hopefully is obvious to you. This number is smaller than this number because you're adding 1, so everything else is identical. You could square both sides and get this, and then subtract n cubed. Check, it's good. So let's draw our conclusion now. So therefore, my original series converges by comparison test. I'm thinking that some of these are going to get more challenging. Let's see. 25. Let's see what how I'm doing on time here. I'm good. 25. Sum n equals 1 to infinity. One plus 4 to the n over 1 plus 3 to the n. Don't want to integrate that. I want to compare. And I'm thinking again, as n gets big, those 1s really don't matter. I'm thinking that this acts a lot like 4 to the n over 3 to the n, which is really 4/3 to the n, which is geometric. I've got r being 4/3, which is bigger than 1, so it's going to diverge. So I just need to show that these guys here, my a sub n's, which are positive, are always bigger than my b sub n's, which are also positive. So let's see if I can show that inequality is true. I want to show that my a sub n's are always bigger than or equal to my b sub n's, or eventually this happens. So 1 plus 4 to the n over 1 plus 3 to the n is greater than or equal to 4 to the n over 3 to the n. All right, let's multiply both sides, like clear out the fractions. So I multiply 3 to the n over here. I get 3 to the n times 1 plus 4 to the n, greater than or equal to, over here I get 4 to the n times this over here, so 1 plus 3 to the n. We haven't seen anything like that before. That's all right, we'll just distribute. So here to here, here to here. So you get 3 to the n plus 3 to the n times 4 to the n is greater than this side, 4 to the n plus, again, distribute through 4 to the n times 3 to the n. And these are exactly the same. These cancel. And then you get 3 to the n is greater than or equal to 4 to the n. And that is not true. 4 to the n is bigger than 3 to the n, as long as n is 1 or 2 or 3 or 4, which it is in this case. So that is not working, right? That's not working. So let me see if there's something else I can compare this to. So this is a good example of one that didn't work out. I've been waiting for one of these. So let me go back here. What was the problem that I had? The problem that I had was that when I did this over here, right? When I did this multiplication here to here, This 3 to the n, then this. I need this side to be bigger than the other side. So maybe instead of using 3 to the n, I use 4 to the n down here to make this side bigger. And so this is such a great problem to show you something. I'm going to continue. I see how I'm going to do it, but I'm going to continue with this logic of trying to make this side bigger. So let's see. Instead of comparing it to 4 to the n over 3 to the n, let me compare it to 4 to the n over 4 to the n. Well, wait a minute. That's just 1, isn't it? Isn't that just 1? So I'm comparing this thing. This is my new b sub n. I want to show that my a sub n is bigger than my b sub n. So I want to show that this is just bigger than 1. And so when I do my clearing of fractions, I get this is bigger than this. And get rid of the 1's, and now it works. Now the question though is, what does this series do? Well, this is just 1 plus 1 plus 1 plus 1 plus 1 forever. This obviously diverges. And so this inequality was true. This held, so it diverges too. So I've shown you how you can do it, but let me take a step way back to the beginning of the problem. Because what happens is you get so embedded in what you're trying to do that you lose sight of something very simple in the very beginning of the problem, which is the very first test on our list of tests, the nth term test. The nth term test says take the limit as n goes to infinity of the sequence you have here. 1 plus 4 to the n over 1 plus 3 to the n. And figure out what happens. Now, we would have to use L'Hopital's rule, because this goes into infinity over infinity. We get derivative of the top, which is 4 to the n times natural log 4. Now, I'm keeping everything in terms of n. We know that when we use L'Hopital, we have to switch it to x, but I think we can do this without going crazy, right? Without losing our minds. Okay, now once we do that, notice that this is the same as limit n goes to infinity of 4 over 3 to the n times natural log 4 over natural log 3. This is just a number out here. But this is a number right here. It's bigger than 1. And we're raising it to a power that's getting bigger, so that thing should blow up. And that means that this thing goes to infinity. And so this limit is infinite. And the nth term test says that if the limit as n goes to infinity of your sequence is not 0, it diverges. And that's not 0. So this thing diverges. I could have been able to determine that from the very beginning of the problem by just doing the nth term test. Now I still got it with the comparison test, but I think that would have been a lot easier. All right, so I would do that, and then I would say, converges by the n, diverges by the nth term test. That was good. I wasn't ready for that one. It got me. So I wasted some time on that. 26, sum n equals 1 to infinity. This one was going to be easy. 1 over 2n plus 3. The only reason this one is easy is because I've told you what you can do in this case. If you have a constant over a linear expression, then this is a harmonic series. So we're going to say this is harmonic, and so it diverges. Right? I would recommend that you go through and try and show this is true. Like I would do this and maybe compare it to this and see if it works, because that's harmonic, especially if you pull the 2 out. Or you could do integral test on this also. Just good practice. 27. Sum n equals 1 to infinity. I always have to check, because sometimes these don't start at 1, so you have to be a little careful. 2 plus negative 1 to the n over n root n. All right, we have an alternating series here. We haven't seen this before. It's the first time since we've started working with series that we saw a -1 up there. So let's try and consider what's happening here. This is always going to oscillate back and forth between -1 and 1. So the top is either going to be 2 plus 1, or it could be 2 minus 1. In this case it's 3, in this case it's 1. So the top is really just switching back and forth between 3 and 1, 3 and 1, 3 and 1 as we move out. And then the bottom is blowing up, it's going to infinity. So definitely don't want to integrate that, because I can never integrate a -1 to the n anyway. So I'm going to try and compare it to something. So I'm thinking like worst case scenario here is that we've got something like this. Like a 3 on top and then n root n. And then that's really just, I can pull the 3 out. 1 over, and then this is really n to the 3 halves. And that's a p series. P is 3 halves, which is bigger than 1. Well, bigger than 1. Which means it converges. Which means I'm going to need to somehow show that this guy right here, which is positive, since this converges, I need to show this, which is also positive. I need to show that this one stays smaller than that one. That a sub n somehow is always less than or equal to b sub n. So I need to show that 2 plus -1 to the n is over n root n is less than or equal to 3 over n root n. Multiply both sides by n root n, they're gone. And then we'll have 2 plus -1 to the n less than or equal to 3. Let's subtract 2 on both sides. -1 to the n less than or equal to 1. You agree with that? This is either a 1 or a -1. If it's -1, it's definitely less than or equal to 1. If it's 1, it's definitely less than or equal to 1. So I'm good to go. So since I found a convergent series to compare it to and the inequality held that I wanted, my conclusion is therefore the series n equals 1 to infinity of 2 plus -1 to the n over n root n converges by comparison. I'm getting a little lazy now. I would like to show you though what would have happened if you would have said, you know what, let me compare it to this. Let me do this in a different color. What if you had not put that 3 there? You would have done 1. Then this would still be a p series. It would still converge. But this over here would change. This would now be a 1. And so when you got to this, you would say 2 plus -1 to the n is less than or equal to 1. And when you subtract 2 on both sides, you get -1 to the n is less than or equal to -1. And this is not going to hold all the time. Because if n is 2, this is 1, and 1 is not less than or equal to -1. So you may have thought, well, that 3 is not that important, but it is absolutely important in order for this inequality to hold. And so why did I use the 3 instead of 1? Well, remember we said the top here, could have been a 3 or it could have been a 1. I went with the bigger one because I was trying to look at like worst case scenario, the biggest this could actually ever be. Okay, I hope that makes sense. If the 3 wouldn't have worked, I probably would have tried the 1 after that to try and somehow get that inequality to work my way. Not saying it would have worked, but. All right, I'm getting close here to the end of this assignment. Wow. All right, 28, sum n equals 0 to infinity. One plus sine n over 10 to the n. That sign in there is making me think that, again, kind of like worst case scenario, what if the biggest this could ever be would be 1. So the top, the biggest it could ever be would be 1 plus 1, which would be 2, and the smallest it could ever be would be 0, right? If sine is -1, sine of n is -1, this would be 0. So worst case scenario, I get 0 on top or 2 on top. So why don't we compare it to a 2 on top, like that. And then pull the 2 out, or you know what, let's not pull the 2 out, let's put the 2 in front and then do 1/10 to the n like that. And this is geometric. The r we have is 1/10, less than 1, converges. I hope that I've made the point that you do not have to go and rewrite this as n minus 1 and all that, because it doesn't really matter. We just want to recognize it's geometric. Although, because it starts at 0, that would have been fine. We'll just leave that as is. Okay, convergent. So it converges. What I need to do is compare this b sub n, which is greater than 0, to this right here, which is actually greater than or equal to 0, could actually be 0. So I have to include the equal there. And since that converges, I want these to be smaller than those, or equal to them. So I want to show that my a sub n's are less than or equal to my b sub n's. So I want to show that 1 plus sine n over 10 to the n is less than or equal to 2 over 10 to the n. I can multiply both sides by 10 to the n, which leaves me with this. Subtract 1 on both sides, and I get sine n less than or equal to 1. That's always true. And so this works. So now I'm going to get real lazy because I'm trying to get this video in under an hour. Therefore, this series right here converges by comparison test. That was 28. See what 29 looks like. Well, as n, let me do the nth term real quick to see what happens. Nth term test. What is the limit as n goes to infinity of sine 1 over n? Well, as n goes to infinity, 1 over infinity goes to 0, sine of 0 is 0. What does that tell me? Not a damn thing. Test failed. I was hoping that would go to something other than 0. So, do I want to try and integrate that? Sine of 1 over n? Do I want to compare it to something? What in the world do I compare that to? Right? I mean, this is not obvious at all. Could we even integrate that? Let's just think about this. Could you even integrate sine of 1 over x dx? Could you even integrate that? I don't know. I don't think so. The only thing that comes to mind here is like integration by parts or something like that. Let's see, how long is my video? Damn it, I'm gonna have to cut this video real quick. When I cut it, I'll come back and finish this. I'm not gonna be able to get the last 2 onto this video, so I'll cut it here. I'll let you think about this. This is a good one. Let you think about it, and I'll come back. Okay, I'm coming back to this problem, and I was looking at it real quick, and I went through the section. I realized, well, hold on a second. We have another test in here that I have not used this entire homework set, but it's part of this section. And it's in your comparison test, there's 3 parts. There's 1, there's 2, and there's a 3rd part. And this last part is what's referred to as the limit comparison test. And this test is really nice because what this 3rd one says is that let's say we're comparing that to this, okay? And remember, this is going to be our a sub n. The limit comparison test says if the limit as n goes to infinity of the ratio of a sub n over b sub n. So you take this and you divide it by this. If that turns out to be a number, where c is a positive number, then whatever this one does, this one does. Okay, so if this diverges, that one diverges. If this one converges, that one converges. Now, there are several problems in this section I could have done using this, but I forgot that this test was in this section. I thought it was in the next section for some reason. So what I need to do is try and come up with something to compare it to, and then take a look at that limit, that ratio. And so I'm going to use something that I really kind of remember from Cal 1, and that's if you look at the sum n equals 1 to infinity of 1 over n, I know that if I put 1 over n under this and do a limit, I know that's going to turn out to be something very nice. But let's first talk about this one. This is a harmonic, and it's divergent. So this is going to be my b sub n, and those are positive numbers. This is going to be my a sub n. Are those positive numbers, though? Well, we know sine oscillates back and forth, right? However, if I plug in like 1, I get sine of 1. And then I'm going to go plus sine of 1/2, then plus sine of 1/3, and then plus sine of 1/4. And I'm going to keep doing this forever, right? Well, these are angles. If we look at the unit circle, this right here is pi over 2. And this is pi. And 1 is smaller than pi over 2. So this first angle is somewhere over here. And then half is somewhere smaller, and 1/3, and 1/4, and 1/5. So all of these angles we're plugging into sine are in the first quadrant. And the value of sine in the first quadrant is always going to be greater than 0. So I know that all of these numbers are positive numbers. So I can use this test. All right, that was an important thing to remember, that these have to be positive numbers. Or they could be 0 also. But so this is true. So I'm going to take the limit as n goes to infinity of the a sub n over the b sub n. And when I do that, 1 over infinity goes to 0, sine of 0, 0. 1 over infinity goes 0, I get 0 over 0. So I could use L'Hopital real quick. Again, I'm supposed to switch to x, but I'm not going to. The derivative of the top is cosine of 1 over n times negative 1 over n squared, chain rule. Derivative of the bottom is negative 1 over n squared. These two cancel. And now if I let n go to infinity, I get 1 over infinity is 0, cosine of 0 is 1. So I'm getting that this limit is 1. And remember, for the limit comparison test, we needed this to turn out to be a constant, a positive number, which it is. If this turns out to be a positive constant, then whatever this series did, this series is also going to do. So therefore, sum n equals 1 to infinity of sine of 1 over n, since that diverged, this one will also, diverges by what we'll call the limit comparison. Test. This is a very nice test. So I would hope that this kind of looked familiar. In Cal 1, if you ever had sine of something over the same thing, and both of these went to 0, This was a very special limit that you learned at the beginning of Cal 1 that they tell you, okay, that limit is going to be 1. Now, I showed it by L'Hopital's rule that it's 1, but that's why I chose 1 over n, is because of this thing. All right, that's kind of cool. So 30, number 30 is going to be the same test. We're going to use the limit comparison test again. And then I think what I might do is go back and take a look at a couple of other problems you could have used the limit comparison test on. Let me do 30. Sum n equals 1 to infinity. N plus 5 over the cube root of n to the 7th plus n squared. And that's not very good looking, is it? So let's try and figure out what we would want to compare this to. How about we compare this to whatever happens if n gets real big over there? Something like, the top would be like n, the bottom would really be like the cube root of n to the 7th. And so what I'm going to do now is instead of trying to figure out what this, get these inequalities and try and do this thing or this thing, I'm going to try and use a limit comparison test instead. So let me figure out what this does. This is going to be a p-series. This is n over n to the 7/3. And this is sum n equals 1 to infinity. Let me see. I can't do simple math right now. This is 3/3 minus 7/3 negative 4/3. So 1 over n to the 4/3. That's a p-series with p being 4/3. That's bigger than 1. This converges. So I have a convergent p-series over here that I'm going to compare it to. But I'm going to do the limit comparison instead of the regular comparison. It's my a sub n, that's my b sub n. Actually, I'll do this as my b sub n. This is positive. This is obviously positive also. So now let me do my limit. Take the limit as n goes to infinity of my a sub n over my b sub n. It's going to look ugly. Let's do this. Let's do n over cube root n to the 7. Let's do that. So I'm using this one up here. And then what I do is before I do my limit, I'm going to flip this one up. So we get equals limit n goes to infinity. See, when I flip this up, I get one fraction. I'm going to have an n plus, I'll do it this way, the n plus 5 up top, that's this. What came up to join it is this one. So times the cube root n to the 7th over, now I had the cube root of n to the 7th plus n squared times, and this n joined it on the bottom. And now what I'll do is again, I don't want to use L'Hopital yet. Try and put some things together here. That's equal to limit n goes to infinity of, watch, I'm going to put these two top of one another, so n plus 5 over n times, and then since these are both cube roots, I'm going to put them all underneath a cube root. And I'll get n to the 7th over n to the 7th plus n squared. And now, of course, if I let n go to infinity, I'm going to get infinity over infinity. In here, infinity over infinity. So I'm just going to go and just on the side and almost mentally do a L'Hopital's rule on this. Okay, so this is like two different limits now. L'Hopital on this, I'm going to get a 1. Times, now I'm going to do L'Hopital on the inside of this, like on the side. I'm doing like limit, n goes to infinity n to the 7th over n to the 7th plus n squared. If I do L'Hopital, I'm going to have to do L'Hopital a few times, and I'll get 1. So I know that this goes to the cube root of 1, which is just 1. So this whole thing, this whole limit turns out to be 1, which is a positive constant, right? This is a constant, it's positive. So that means that whatever this series did, that one does also. So therefore, it converges. Therefore, series n equals 1 to infinity, n plus 5 over cube root n to the 7th plus n squared converges by the limit comparison test. So let me see what other ones we could have gone back and done. Let me see here. How about number 26? This is the one I said we could show its harmonic and just be done with it. On 26, sum n equals 1 to infinity, 1 over 2n plus 3. If I compare that to a harmonic series, if I compare that to 1 over n, I know that this diverges. I'm going to go through this very quickly. And this is positive and that's positive. So if I take the limit as n goes to infinity of this guy, 1 over 2n plus 3, over this one, 1 over n, and I flip, and I get n over 2n plus 3, then I do L'Hopital, I'm going to get 1/2. And this right here is a constant and it's positive. And that's what I need for me to draw my conclusion. So whatever this one does, that one also does. So that one would diverge. And we knew that. Let me see if there's another one that we could have done using that one. Jeez. Could have done 25 also, that way. For 25, we had 1 plus 4 to the n, 1 plus 3 to the n. Remember that one? And that one we did by the nth term test. But let me just show you if we compare it. If we compare it to that 4 over 3 to the n, this is a divergent geometric series. So we would do limit n goes to infinity of this guy over this guy. I'm going to write it this way, which is limit n goes to infinity, and when we flip, we get 1 plus 4 to the n over 1 plus 3 to the n times 3 to the n over 4 to the n. And then I could split this up and do something like limit n goes to infinity of 3 to the n over 1 plus 3 to the n times 1 plus 4 to the n over 4 to the n. And then when I do L'Hopital, I can do L'Hopital, since it's product, I can just do L'Hopital on each one. So I would get something like limit n goes to infinity. L'Hopital on this would give me 3 to the n times natural log 3 over 3 to the n natural log 3 times, this one would be 4 to the n natural log 4 over 4 to the n natural log 4. And then these cancel, and then that's a 1, and then that's a 1. So this all equals 1, which is a constant, and it's positive. So whatever the original, whatever I compared it to does, this one does. Remember, I compared it to a divergent geometric series, so that's going to be divergent. See if there's any others that I would want to do that way. I think that's probably good enough. Just to show you how that's just to show you how that limit comparison test works. All right, well, that's 8.3. I hope that all makes sense. Good to go.